So R will accept if some machine here. So all the elements of this language, they are of machines that whose languages are empty, right? All the members of this language, they are machines that accept no strings, right? The L of B is just the empty set, okay? So if R accepts this, then the language of B is the empty set, okay? So if that's the case, now given the way we set up B, that means that M has no accepting computation history, when the W goes in, okay? Now if you have no accepting computation history, what does that mean in turn? Well, it means that M did not accept W, okay? Right? So we can conclude that. Now, if therefore S rejects this, right? So when R accepts that, we conclude that S rejects this. Okay? So whatever R's doing, if it's accepting, S will do the opposite. All right. Now, if R rejects that, what does that mean? Well, that means that the B's language is non-empty, right? It's not the empty set. Now that means there's only one string that B can accept. That's because the way we set it up. Because there's only at most one accepting computation history for a deterministic Turing machine. Okay. All right. Now there's only one of them, and so that means that the only string that B can accept, there's only one of them, is an accepting computation history. So that means that M accepted W. Okay, therefore M must accept W, right? And so that means that you return that S accepts that, because we know M accepted it. So therefore S conclude that M accepts that. So either way, S is either accepting or rejecting, and therefore it's a decider. And that's a contradiction, because we know that this is undecidable. That's the contradiction. And so we go back and negate our original assumption in the proof by contradiction, and that is that this must be undecidable. Okay. Let's say a little bit of a diagram. What's this for? This is an example of B looking on, and what's this tape? What's this string here? This is X. This is X, which is so we've got like 4 symbols in our configuration here with state, okay, and separated by hash marks. Okay. All right. So that's effectively the end of that proof. So what we do now, we change tack a little bit, and we start. It's more discussion as a kind of lead-in to the next proof, which will occupy the following session. Right. Now, so it's sort of lead-in, a bit of commentary. Well, not on this, but in general. So now we've been using the technique of reduction, right? This previous proof, using computation histories to prove undecidabilities of certain problems. Okay. Well, that's just what we've been doing. Let's see. Now we're talking about future or past here. A bit confusing. Okay. We can use. All right, future. All right. So we can use the same reduction technique using computation histories, and we can prove certain languages are undecidable, and these languages are related to context-free grammars and push-down automata. Right? So So that's a comment for the future. We can use. Right. Now, if you go back page 173 of your text, have a look at theorem 4.8, and what was that? It was this, I think. We showed that E for empty, that this particular language is actually decidable. Okay? Let's see. So what was this theorem about? So it presented an algorithm. Algorithms and Turing machine, same thing. Okay? So in other words, we showed the existence of a Turing machine that decides this language. And if you translate that language into a computational problem, in other words, reword it, so this Turing machine is deciding whether a particular context-free grammar, call it G, generates any strings at all. In other words, it decides whether, given a grammar, is its language. Remember, a language of a grammar is all those strings that the grammar can generate. Right? So this language is decidable. That means that there is a Turing machine that can decide whether, for a given grammar, whether its language is empty. Okay? Right. Now, okay. So that's an example of the sort of thing we'll now start doing. Now there's a related problem, also concerned with grammars, CFGs, context-free grammars. But this particular language is undecidable. Here it was decidable. Okay? So we're getting these interesting contrasts, distinctions. In certain cases, the same kind of language, well, the same kind of context. For example, context here, context-free grammars or PDAs. And sometimes it's decidable, other times undecidable, which is interesting. Right? So now there's a related problem concerning with CFGs where language is in fact undecidable in the context of CFGs. Now, what is that problem? Well, try and find a Turing machine that can decide whether a given context-free grammar G can generate all possible strings. That's the problem. And we'll show that that problem is undecidable, or is unsolvable, can't do it. Or if you talk in terms of language, then language, here it is here. So we'll just call it all. So for all strings, all possible strings given your input alphabet, in other words, capital sigma. So sigma star here. Okay. So it's the set encoding of all grammars. That's your string in the language. Okay, where G is just some context-free grammar, such that the language of that grammar are all possible strings. So this grammar here can generate all strings. Okay, given the input alphabet, on your input string, your W, all possible, your capital sigma is then all possible symbols of capital sigma. Right? Now we will show that, well here it is, theorem 5.13, this language here is undecidable. Okay? And again, again we'll use proof by contradiction in a similar sort of way as before, but there's a twist. Okay, step back.